Okay, so here's what we were talking about last time. We were talking about using polar coordinates to make a change of variables function, right? So here's such an example. This is the polar coordinates function. The conversion formulas for polar coordinates interpreted as a function that takes r and theta and gives you x and y, right? So that's the first sort of, choice. So, reinterpret these polar coordinates formulas as a function. Now, second, using it as a change of variables function, right? So, pulling back, this domain pulls back to this domain, right? Which is much more desirable because it's a rectangle, nothing curved, no corners to hit as you slice, all sorts of great things. So the last observation that we made, aside from that you can do something very similar to this for both cylindrical coordinates and spherical coordinates, is that, once it comes time to actually slicing up this pullback domain, you can see that slicing process over here. Right? You don't really have to, useful though it is to think of this as a pullback, it really is a pullback, and to use the formulas for that we have from change of variables, you don't really have to draw that picture. Everything you need to see about this slicing process, you can see it over here. Right? And so if we don't have to draw an extra picture, that's a good thing, right? It saves us trouble. It saves us the potential for accidentally, making a misinterpretation or something. So rather than doing the slicing over in this new r theta space that we've pulled back to, we're going to effectively infer what we need to know about that slicing right here in xy space. Okay. All right, so we talked this through last time. Here's the first theta slice. That's where theta is equal to 0, and our theta slicing continues along, blah, 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 like this until we get to the end. That's our last theta slice, where theta is pi over 2. Just think polar coordinates. That's 0. That's pi over 2. Okay, so theta goes from 0 to pi over 2. Right now, on a given theta slice, what's the range of values of r? I'll do this in blue. So the r values. Well, we start there where r is clearly 0. We end here where r is clearly 1. So r goes from 0 to 1. Okay, so this is, when people say they're going to do an integral in polar coordinates, this is really what they're talking about. A lot of people doing integrals in polar coordinates aren't even really thinking about the fact that they're using a change of variables. It's certainly a good way to think about it, but you don't have to actually consciously be thinking about it that way. You just, remember that dx dy is stretching factor times dr d theta. Don't forget your stretching factor is r. And then in the slicing process, come up with these bounds by the slicing process we talked about, namely slices corresponding to the certain variables as we just discussed. Okay, so let's see another example. Let's suppose you're interested in this domain. I want to compute the mass of this domain or whatever. So we're doing some sort of a double integral here. Well, we could do this in rectangular coordinates. We could slice like this, for example, rectangular slices, and of course that's going to give you square roots in your inner bounds. That means you're going to have square roots in your outer integrand, and that means that this has the potential to be a nasty integral. On the other hand, let's do this in polar coordinates. This is what theta slices look like. Not hard to persuade yourself that theta starts at 0, goes around, ends at pi. Right? And then a given fixed arbitrary theta slice, range of values of r starts at 0, r ends at 1. And so that gives us, let's see, where would I have this? Here we go. So theta goes from 0 to pi, r goes from 0 to 1. Everybody happy? Right. Now, don't forget that, like I said yesterday, it's real easy to spend all your time thinking about these bounds, drawing the picture, thinking about the slicing process, and to forget about that R right there. It's so easy to forget it. Right? It's easy to remember it, but it's also easy to forget it. Right? And that's the more important point. So, again, I remind you, when you write down, when you sort of make the switch to polar coordinates, don't forget to stick that R in there as you are writing dr d theta. Don't ever write down the one without the other. Just as a tool against, this hard to nail down problem of oopsing. Okay. So now that said, don't forget you have to plug in for the integrand as well. X is r cosine theta. So x squared is r squared cosine theta. Likewise, y is r sine theta. Okay. So this simplifies to r squared. And again, if you're not paying attention and you spend a bunch of time thinking about the bounds, doing trig, converting the integrand, it'd be real easy to forget the extra factor of r right there. Altogether, of course, then your final integrand is r cubed. Yeah? Everybody good with that? Okay. All right. Okay, so one more example. Suppose this is our domain. Here, so we have an off-centered circle. So the circle is centered at A and of radius A on the x-axis and radius A. So this side swipes the y-axis at the origin, right? And I suppose that's our domain. Well, again, you could do this in rectangular coordinates, square roots everywhere. Highly undesirable. So let's do it in polar coordinates. Now, common mistake, lots of students make this mistake, is to think, okay, well, let's see, here's us going around, right? And a lot of people would say that theta goes from 0 to 2 pi. Well, this is absolutely wrong. There's this urge, this psychological need in some sense for students to think about theta as being measured from the center of whatever round thing they might happen to be dealing with, right? And wouldn't it be nice if that were always the case? But it isn't, right? Theta is measured from the origin, right? This circle, this disk that is our domain is off center. So again, there's this temptation to want to think about, how do angles look from there, but that's got nothing to do with polar coordinates. Polar coordinates are measured from the origin, right? So this is what a theta slice looks like, right? So be super careful with that. Again, very common mistake. So with the understanding that that's what a theta slice looks like, let's think about the different values of theta where we actually get slices, and you can see they keep getting sort of shorter and shorter as theta increases. Right? And if you think about, just how far can you go? How high can theta increase before it's not hitting the domain anymore? And, it's kind of the very last slice is going to be going straight up. So technically straight up doesn't really quite hit anything. Right? But anything less than straight up will hit a little bit of disk. Right? Okay, so pi over 2 is the last value, and go in the other direction. It's sort of the opposite. They get shorter and shorter as you approach negative pi over 2. So this last, the first slice, I guess you'd say, is negative pi over 2. So for this domain, theta goes from negative pi over 2 to positive pi over 2. Everybody clear on that from the picture? Okay. All right, and let's see, where's the... There we go. So, theta, negative pi over 2 to positive pi over 2. Okay. So, now we fix a value of theta. Now, on that value of theta, what's the range of values of r? Well, r starts there on that point where r is clearly 0. No problem. R ends there. And here it's not immediately obvious. What is r at that point, right? So we have to, instead of sort of picking up freebies like we have in all of our previous examples, let's go back to our previous method of realizing that if you want to understand bounds are determined by points. Points are on curves. Curves have certain equations. And this is a chapter 1 exercise. If you take this circle, right, centered at A on the x-axis, radius A, write down the equation, rectangular coordinates, algebra 2. Right? Then convert into polar coordinates. What you will get is this equation. And so in this equation, we need to solve for r. It's right there. Already been done. And so that upper bound is going to be 2a cosine theta. Everybody happy with that? Okay. So, yeah, R 0 to 2a cosine theta. Okay. Yeah. Don't forget your RD theta. Again, super easy mistake to make. I've done it myself many times. That's why I'm making a big deal out of it. Okay, so same argument can be made in cylindrical coordinates, right? So the point of view that I'm emphasizing now is that even though you can view polar coordinate integrals as being you're really doing change of variables. I mean, you can kind of ignore the whole change of variables aspect of it once you've got your stretching factor stuck in there. Everything that you need to see about the pullback domain is visible in the rectangular domain. So just interpret the slices appropriately, and you can find all your bounds right there in the rectangular domain. So here's what coordinate slices look like in, where am I? There we go. This is what slices look like for cylindrical coordinates as seen in rectangular coordinates. So a constant value of r, otherwise known as an r slice cylinder. Right? Constant value of theta is a half plane hinged on the z-axis. Right? And a z-slice, just like in rectangular coordinates, constant value of z is a horizontal plane. Okay. So just keeping in mind that this is what slices look like. Slice, in this sense, slice up your domain if you're going to do it in cylindrical coordinates with respect to these slices. Okay. So here's an example domain like this. Now, you could do this in rectangular coordinates, but if you do this in rectangular coordinates, notice there's a circle in here. Right? That means that at some point, either y is going to depend on x or x is going to depend on y, and you're going to have square roots, which is undesirable. Okay. So let's do this in cylindrical coordinates. Now, here's our options. Keep in mind there's 6 different ways to order differentials. I have some really good news. Most of those 6 options are bad and should mostly be ignored. There's really only 2 realistic options for orders to go in with cylindrical coordinates, and those are r dr d theta dz and r dz dr d theta. So the idea here is that the polar differentials need to stay together and in that order. It's just so much easier to view r as a function of theta than theta as a function of r in almost all cases. I think if I went to a bunch of trouble, I could find a counterexample where doing it a different way would be preferable. They're very hard. They're sufficiently rare that I think it's, your best strategy is to ignore those possibilities. Just stick with, always pick one of these. So either do your z slicing and then polar slicing, or vice versa. Okay. So in this example, I'm going to do it this way, no particular reason. So let's think about the range of values of z. Well, our z slices look like that. So our first z slice is down here, where z is clearly 0. Our last z slice, well, this is a cone that tops out at 1. So our last z slice is 1. So z goes from 0 to 1. There we go. So z, 0 to 1. Yeah? Okay. So now we're going to focus our attention on a particular value of z. We're going to look at a single z slice there. And on that z slice, again, couldn't care less about it. We're going to get to all those other points in the solid for other values of z. We're going to look at one value of z at a time. And for this value of z, next question, what's the range of values of theta? All right, so how do we theta slice this z slice? Okay, well, by the way, here's a better picture. Keep in mind that a theta slice looks like that. So a theta slice of this existing z slice, and what happens if you take a horizontal disk and slice it with a half plane? Well, you get a little line segment like that. So that's what a theta slice of our z slice looks like. Is everybody happy with that? And now you just have to think, okay, so for what values of theta do we get such a slice? Well, the first one's going to be where theta is equal to 0, and then, look, this goes all the way around the z-axis, and so we're going to end, when we get back to where we started, we're going to end at theta equals 2 pi. That's a geometric appeal, right? We have a picture of what our domain looks like, and that's what's going on. Is everybody happy with that? Any questions? Okay, so theta is 0 to 2 pi. Oh, here we go. Yeah, theta 0 to 2 pi. Okay, next, what's the range of values of r? So we're going to look at a theta slice of our z slice up here. There's a theta slice of our z slice right there. On that slice, what's the range of values of r? Well, okay, so we start at that point. That point's on the z-axis. Any point on the z-axis, the cylindrical coordinate of r is clearly 0. So we start at r equals 0. More interesting, what about that point? Our last r slice of our theta slice of our z slice. What's the value of r at that point? Well, so again, not immediately obvious. You can't just look at the picture and just see it, right? So what we have to do is we have to figure out, well, the bound corresponds to this point. That point's on this surface. What is the equation of that surface? Now this becomes a chapter, a chapter 2 problem, I guess. Chapter 1, chapter 2, depending on how you want to look at it. So I'm going to leave this as an exercise for you guys, but this surface here has the equation r plus z equals 1. So think that through, right? How would you come up with that? Make sure that you can come up with that, on your own, without knowing the answer in advance. What would be your reasoning process? How would you justify that on an exam, for example, right? Where you came up with that equation? Okay, right. So here we go. We're trying to figure out the upper bound for r. The bound is determined by this point. This point is on this surface. That surface has this equation. I'm looking for r. So solve for r in the equation. R is equal to 1 minus z. So r goes from 0 to 1 minus z. Like so. Everybody good? And it's the same process, in all the other kind of examples that we've done. It's just we have to interpret slices appropriate to the coordinate system that we've decided to use as our change of variables function.
Mm-hmm. Go up one second.
Mm-hmm.
All right.
Mm-hmm. Yep. Okay, so spherical coordinates. Same deal. Right? Again, the main thing you have to keep in mind when doing spherical coordinates is what do the slices look like. These are they. Unfortunately, these are a little weirder to work with. It's a pro and a con, but I'm going to lead with saying this is a con. That's a pretty weird kind of a slice, right? When rho is constant, a rho slice. Oh man, it's hard to figure a knife making a cut like that. So thinking of the slicing process in spherical coordinates, depending on how you order the differentials, can be pretty darn confusing. That's the bad news, right? So anyway, this is what a rho slice looks like. This is what a phi slice looks like, constant value of phi, right? This is what a theta slice looks like, just like in cylindrical coordinates. So that's the bad news. The good news is the other options are so geometrically challenging and weird that there's really only one reasonable ordering of the 6 possibilities, and you should always do it in that same order. Again, I think if I went to a bunch of trouble, I might be able to manufacture a really weird counterexample where it makes sense to do it the other order. But overwhelmingly, most common is to do the differentials as follows, and you should just always do them in this order. Of course, don't forget your stretching factor, right? We don't ever write down our dV without leading with our stretching factor. And that's the order. d rho, d phi, d theta. Always do d theta on the outside. By the way, that's pretty easy to motivate. I mean, of these three choices, that's the easiest slice to think about geometrically. It's a flat slice. It's the only one. Seemingly obvious first choice, right? Now, inside of that, what does a phi slice look like inside of that theta slice? Well, it's a straight line, right? Whereas, by comparison, a rho slice of this theta slice would be curved and therefore a little harder to work with. So that's why we don't do that next, and we do d phi next. And then process of elimination, we do d rho last. Okay. So anyway, that's for the purposes of this course, always the order that you should use. So always write down your spherical differentials like this: rho squared sine phi d rho d phi d theta. As such. Okay. All right. So here we go. Here's an example. Let's suppose I want to do an integral on this domain here, the solid ball offset from the origin, right? Centered at A on the z-axis with a radius A, so that again it touches the origin, kind of sideswipes the xy plane at the origin. Okay, so there's our domain. How do we do this? Well, you could use rectangular coordinates, square roots everywhere. The nightmare of square roots. Horrifying prospect to think of working it out that way. Right? Now you could use cylindrical coordinates, right? But then you're either going to have r as a function of z or z as a function of r. And if you write down the equation for this sphere in cylindrical coordinates, you're going to either have a square root giving you r as a function of z or vice versa. Right, so again, wanting to avoid square root, cylindrical coordinates is bad here as well. Spherical coordinates turns out to work out actually pretty okay. Let's see how that plays out. So again, here's our ordering. We're going to start with our theta slices, and on this solid, what's the range of values for theta? Well, a theta slice, half plane hinged on the z-axis, and so you see we get a slice like that. Now this solid sort of envelops that part of the z-axis, so these slices are going to make it sort of all the way around, if you will. And so theta is going to go from 0 to 2 pi. That's a geometric appeal. Everybody happy with that? Okay. All right. So now we're going to fix some value of theta. All of our attention now is on that single value of theta. Don't worry about what the sphere is doing over here. We'll get to that for a different value of theta. Right now we're thinking about this value of theta. On that value of theta, let's draw what our slice looks like. Now here it becomes a geometric challenge. What does it look like when you take this sphere and then you take a vertical but angled slice that you're looking at from a weird perspective angle? How can you see what that thing looks like? It is geometrically challenging, right? So again, get a sack of oranges and a knife and start cutting it up, right? And give yourself the practice of looking at three-dimensional models of the kinds of things that we're talking about here, right? And then it's a little messy, but then you can eat the results. We should all be eating more fruit anyway. So this is a good exercise. Sack of fruit is cheap. And here's what that slice looks like. It's a half disc. Now, we're going to have to draw some pictures on this half disc, right? Because on this half disc, we have to start thinking about the range of values of phi. And I have to recognize this is, we're looking at that from a weird angle, and this is a hard picture to draw. So I have a trick on this that I want to encourage. Keep in mind this is a theta slice, so this is for a particular value of theta. For my own sanity, right, what I do when I feel like I need it, when I find my picture, I'm looking at it at a weird angle, just take the theta slice, because that's all we care about anymore anyway, right? We don't care about these points over here. What's going on there. We'll get to those later for different values of theta. On this one theta slice that we now care about, just redraw that theta slice, looking at it straight on. Right? So, this is, as seen from exactly perpendicular. So there's the z-axis, and this is, I don't know, you might want to call that the r-axis or something. Not that it's really an axis, but that's, let's see, where's my, for this theta slice here, that's that line, and you can see why I call it the r-axis, because it's pointing in the direction of increasing r. Okay. All right. So rather than trying to figure out how to make sense of understanding phi slices as seen from an angle, which can be confusing, just look at this picture right here. This is optional. You don't have to do it this way. I think it's highly desirable. Suit yourself. Okay, so on this slice, and again, here is what our theta slice looks like. Here's what phi slices look like. Phi slices emanate from the origin. Again, don't make the classic blunder. Classic mistake is to say, okay, so we'll look at the phi slices like this. Students have this urge to think of angles emanating from the center of whatever they're looking at, and that's not how it works, right? Phi is always an angle that comes out of the origin, independent of what might be most convenient, independent of our wishful thinking. Right? Okay, so this is what a phi slice looks like, and there's the first one at 0, and they keep getting shorter and shorter as phi gets closer and closer to pi over 2, and the last slice is there at pi over 2. Everybody see the picture? Everybody happy with that? By the way, I've said this before, let me say it again, that this course is unavoidably geometric. Right? There is no algebraic way to just kind of figure stuff like this out. You've got to have a picture. Right? So if you're not very good at drawing pictures, get good at drawing pictures, right? Practice drawing pictures. Come talk to me about how to get better at drawing these kinds of pictures. And another point I'd like to make, notice that the pictures that I have in the book here, they're all pretty big. Right? It's pretty common for me to see students making pictures that are, about like this. And they're, doing the... I get that on exams all the time. Right? What can you tell from that? Right? It's really hard to read what's going on there. Which, for one thing, take pity on me, but take pity on yourself, right? This is supposed to be, something that's helping you understand the geometry of the problem you're looking at, right? So if you hinder yourself with a teensy-weensy little picture, it is going to make it harder. So give yourself a nice big picture to work with. Okay, so let's go to where we have this written down. Okay, so we agreed already that theta goes from 0 to 2 pi, and as we just argued, phi goes from 0 to pi over 2. Right? Everybody good? Okay. So now, range of values of rho. So we're going to pick a phi slice. There's a given phi slice. Range of values of rho. Okay, well, rho starts there. That's the origin. Rho is clearly 0. So, easy starting point. The last value of rho is going to correspond to that point. And again, it's not immediately obvious exactly where that is. So we have to think it through. Think about what geometric objects is this on and what algebraic equations do I have for them. So, well, this point is on that curve. What do I know about that curve? Well, okay, let's not forget we're looking at a single theta slice. That curve came from this picture where it's a slice of a sphere. So the point that we're looking at, yeah, it's on that curve, but more to the point, it's on that sphere. So we need to find the equation of this sphere in spherical coordinates. Okay, so again, this is a flashback to Chapter 1. Remember, we spent some time in Chapter 1, how do you find the equation of this or that in a given coordinate system. So you've got to go through this process here. Here's the equation in rectangular coordinates. That's Algebra 2. right? Then play the game. Again, just a reminder, I think it's always good to be on the lookout for stuff like that you can instantly just rewrite as rho squared. Right? That makes your life, rather than just reflexively plugging in x equals y equals, all in terms of spherical coordinates and then doing lots and lots of trig. That's a real time saver. By the way, that is something I saw a lot on the midterm exam. The first midterm exam is students missing this little opportunity here on I think it was number 2. Anyway, go through and find the equation, and there it is. That's the equation for this sphere. Now, keep in mind, the reason we're looking at the equation for this sphere is we're looking for a rho bound. So, in the equation for that sphere, we need to solve for rho. Rho equals what? So, solve for rho. Oh, good deal. We've already solved for rho. There it is, 2a cosine phi. And that's our upper bound here for rho. Rho 0 to 2a cosine phi. Everybody happy? Now you can see these problems have been getting sort of more and more involved as we've gone through the section here. And so now, hopefully you'll see even more so how, you can spend a bunch of time worried about these bounds and thinking about the slicing process. And, maybe you write down these differentials just as a visual reminder of what order you're doing the slicing process. And it's so easy to forget the rho squared sine phi. It's so easy to do that. So I beg you, write this down all at the same time. The whole thing. Rho squared sine phi d rho d phi d theta, all at once. Okay, how are we doing? Anybody have any questions about it? Yeah.
How did you go from the top line to the bottom line?
Yeah, okay, so I've got, that's rho squared.
Oh, okay.
And there's another rho squared, and that gives me the rho to the 4th. Yep. Anybody else? So, a lot of practice is helpful in getting good at doing integrals, in spherical coordinates or in polar coordinates. So you're going to get that practice, obviously, on the exercises. And there's just, a bunch of things here, a bunch of shapes, a bunch of different domains where if you choose the appropriate, the most clever coordinate system for the, whatever the specifics of that question are, then the question becomes a lot easier. So, yeah. Okay. All right. So, moving along, scalar line integrals. Here's the kind of problem that we're going to consider in this next section. Suppose we want to do an accumulation problem, like we're computing a mass. Here's a one-dimensional rod thing here, of which I want to compute the mass. Trouble is, this is now this is in three-dimensional space, and yet it's not really a triple integral, right? I'm viewing this thing as being a maybe I'm viewing it as being kind of intrinsically one-dimensional in the sense that maybe I know density as mass per unit length, right? If it's a really thin rod. So I want to treat it as a single variable integral, but it's in 3 space. But kind of can't. So what do you do? I guess I could treat it as a triple integral because it's in 3 space. But it's not really, but it's really one-dimensional domain. So this is a mismatch situation. It's quite awkward, right? So we're going to have to come up with yet another kind of integral. And so this is going to be our 4th kind of integral. We've got single variable integrals, double integrals, triple integrals so far. And then, sure, polar coordinates, spherical coordinates, all that kind of stuff is really just techniques for computing these, right? So, but up to now we've got 3 different kinds of Riemann sums that match to different kinds of questions. Here is one that matches with none of these 3, so we're going to make a 4th. This is called a scalar line integral. Line, I suppose if we want to be more careful about it, we'd call it a curve integral or a path integral. Some people say path integral. I've never heard curve integral, but overwhelmingly people say line integral, at least in my experience. And a little bit sloppy. It just means it means curve. Okay, so scalar line integral, I'm going to pretty much punt on this one for the moment. There is a different kind of line integral, as it turns out, that we're going to see later. I need to distinguish between the two different kinds of line integrals. So why we call this a scalar line integral, let me come back and talk about that a little bit later. For the moment, just take it on faith. This is, I think, a good choice. Call it scalar line integral. Okay. So here's our situation. We've got this curve. Right, and I want to chop it up into little pieces. And make an accumulation argument, right? The total mass of this rod, it's the mass of that one piece, plus the mass of this piece, plus the mass of the next piece, etc., etc. Here's the ith piece, right? I'm going to add the mass of that thing, and I'm going to keep going until I get all the way to the end of the rod. So I can make an accumulation argument in that way, which is kind of reminiscent of single variable integrals. Of course, this is very different because it's in 3 space. Okay. All right, so now let's take a closer look at this little piece of curve. That little piece of curve. I need to know a couple of things about that little piece of curve. I need to know how long it is. If I'm going to talk about the mass on this little piece of curve, I need to know, I'm going to be eventually talking about mass per unit length times length, so I need to be able to talk about the length. So how long is that little piece of curve? And we're going to have to work some details out there. That's an issue. Okay. Other thing I need to know about this piece of curve is, where is it? Well, I'm going to have to talk about a sample point. I'm going to call it just xi. So some arbitrary point picked in that ith sliced up piece of curve. Okay, and with that in mind, here's how we're going to define a scalar line integral. It's our chop it up, add it up strategy. We're taking this curve, we're chopping it up into little pieces. On each piece, we're going to take some integrand. Now, I like the mass metaphor. Let's pretend we're computing mass. So, density, mass per unit length, computed at where the curve is. Keep in mind that where the curve is defined by that point xi. So there's mass per unit length that we're multiplying by length to get our estimate of how much mass there is in that piece. Adding up gives us our estimate of the total mass. Taking a limit, hopefully fingers crossed, as long as the function's appropriately nice, we hope that those round off errors go away, thus giving us the actual value of the mass or whatever it is that we're computing here. So does everybody see how this, it's morally equivalent to Riemann sums we've written down previously? It's just, in this different context. Everybody good? Okay. So the notation, I think, is very plausible. ds, representative of the fact that we're multiplying in the Riemann sum every density times a piece of length. Right? Delta S. So, ds. Right? We're adding up with one index and taking a limit. So, one integral sign. As we've done before, I've got to tell you what the domain is. Several kinds of integrals we've defined previously. We've just written the domain as a subscript. Right? And then, of course, I've got to tell you what is this function with which we compute densities in order to compute mass. So I've got to tell you what that function is. So very believable, very sort of expected notation there. Pretty plausible. Everybody happy with that? So henceforth, I'm going to use this notation, right? And I encourage you to use notation like this. And as you're developing your Riemann sums, go ahead and feel free to use differential shorthand like I've got here. But whatever you do, make sure to remember that anytime you see something that looks like this, it's just a shorthand. What you're really doing is you're writing down a Riemann sum. You're really executing a chop it up, add it up strategy. Taking your domain, chopping it to little pieces, looking at each piece one at a time, computing what you're interested in on that piece because it's easy on little pieces, and then adding up over the whole thing. By the way, remains to be seen how to compute these things. Right, how do you is there a fundamental theorem of calculus for scalar line integrals? No comment just yet. We'll get to that in a few minutes, right? So right now I just want to talk about that this represents a Riemann sum, chop it up, add it up strategy. Okay, so let's apply this strategy, this notation, to some examples. Here's one. This is I thought of this example when I was living in a house that I was renting that was kind of out in the country. Long story. But it was on like 4 acres or something, and the driveway for this house was a couple hundred yards long. And it occurred to me, if we have a deep snow, and if I have to shovel this driveway, my gosh, what a nightmare. How much snow am I going to have to shovel? How much weight? You just kind of want to brag about how much work you're about to do, right? I'm going to move 50,000 pounds of snow. It'd be nice to know what that number is, right? So I started thinking about, okay, well, how would one compute the amount of snow on this driveway? Okay, so here's the situation. Our driveway is about like that. Some curve, right? Certainly, you'll agree that the total amount of snow is the sum of the amount of snow on each piece, sitting over little slices of the driveway. So if I were to break up this curve, by the way, I'm thinking of the driveway as effectively being a curve. If I were to look at a little piece of curve there, that little piece of curve corresponding to a little piece of the driveway with, I know what the width of the driveway is, and if I take a little piece of curve of length ds, the amount of snow sitting on top of that slice of the driveway, if I add up over all the slices of the driveway, that'll give me a total amount of snow. Okay. Okay, now how much snow is there on this piece? Well, it depends on how deep it is, right? So I'm going to need to know depth. So we're going to need to know, in this situation, I'm going to try to draw a snowdrift here. This is greatly exaggerated just for visual sort of convenience. Let's suppose that it's like this. Right, so it's higher. It's higher over on one side of the plot, right, and it's lower on some other side of the plot. That's pretty physically plausible, right? I mean, depending on tree placement and wind and stuff like that, you could easily have highly variable depth. Okay. So on that little piece, though, looking at this little piece of the driveway, teeny little bit of area there, I can talk about, well, what is the depth of snow on that little piece? Call it h. So height is going to be a function of position, x and y. And if you know what that depth is, and you know the width of the driveway, and you know that you're looking at a little piece of length ds, h times w times ds would tell you how much volume of snow there is sitting over that little piece of driveway. Okay. So this, easy to write down thing, height times width times ds, that is what we're adding up over the entire curve. And so that scalar line integral will compute the total volume of snow sitting over that driveway. Thankfully, I never had a big snow while I was living there, so dodged a bullet there. But anyway, this is how I would have done it. Questions? Everybody on board? Feel free to ask a question. Everybody understand the context here? All right, we've already talked about this next example, so let me just go through this quickly. If you're interested in computing the mass of a bent rod, like the very first thing we were looking at, well, the total mass is the sum of the little pieces of mass that you get when you chop up that curve into little short lengths. And on any given length, mass is density times length. Okay, so easy way to motivate that mass is computed with a scalar line integral. Okay, so the big looming question, we see that this construction, this scalar line integral construction, applies to different applications, different quantities I might want to compute. Again, anything that's accumulating, any accumulating quantity. How do you compute them now? Big question. Okay, so we're going to use an idea that we've seen before. We're going to use the change of variables idea. You remember the big strategy behind the change of variables idea was, what if we have a domain that we don't like? Now, the reason we didn't like domains when we were doing change of variables was because they were curved and had corners that I was slicing through, and they were bumpy and wiggly in weird ways. We just didn't like the shape of them. Right? Here, I mean, my reason for disliking this domain is arguably a little deeper. It is dimensionally awkward, right? It's a one-dimensional thing in a three-dimensional context. I just can't deal with the dimensions. It's just not a Riemann sum like we've had before. So we're going to try to figure out how to deal with that dimensional awkwardness. And specifically, when I say I'm going to try to do a pullback argument, just like with change of variables, I want to view that as being the image of something I like better. I would like to specifically view it as being the image of something that's not dimensionally awkward. So my curve, C, it's a one-dimensional thing. I'm going to view it as being the image of a one-dimensional thing, but in a one-dimensional context. So I'm going to take a curve, a one-dimensional set in 3 space, view it as the image of a one-dimensional set in 1 space. And then when I do a pullback, right now details, of course, have to be worked out. This is just kind of strategic thinking here. But when I do a pullback through this x function, whatever that is, the integral that was over this dimensionally awkward green curve will become an integral on an interval on the t-axis. It's going to become a Calc 1 integral, which we're really good at, right? We totally know how to compute those. We have a fundamental theorem of calculus. We know how to do that. So that's the strategy. So the big missing link, what we don't have not yet identified, is how do I do this? How do I view a curve in space as being a function of t? Oh, wait a minute. We do know how to do that. That's a parametrization. Yeah? And it just happens to be that the thing that we need in order to be able to do, a pullback strategy, kind of a change of variables, modified, adapted to this circumstance, it's something we already have and we are actually fairly good at doing, finding parameterizations. Okay, so step 1, when you want to compute a line integral, whatever your curve is, parameterize it. Right? And then, of course, in the process of parameterizing, you got to figure out what those bounds on, what's the starting value of t, what's the ending value of t. Okay. All right, next question. Of course, we're going to do some examples. Next question. Okay, so I've got this curve on which I want to do an integral. Just like with change of variables, I'm going to take my pullback domain. I'm going to chop up my pullback domain into little pieces. Right? In the process of chopping up that pullback domain, I'm effectively, by pushing forward, chopping up the target into little pieces of who knows what size, probably not all the same. Right? Depends on the parameterization. My parameterization might speed up and slow down, so who knows what kinds of sizes these pieces are. And what I need to get a handle on now is how big are these pieces, or more specifically, what's the relationship between the size dt and the size of that little curve ds. All right, so a little piece of the t-axis, by way of this parameterization, is going to turn into a little piece of the curve. What's the stretching factor, right? I know if I have ds as part of my line integral, I need to rewrite ds in terms of dt. I need to write it as something times dt. What is this stretching factor that I multiply by dt so that I can plug in and get rid of ds? Okay, so we're going to get this by computing ds. This is pretty straightforward calculation. I am going to introduce, because the opportunity is here, I'm going to introduce a new object. I'm going to introduce a new object here called dx vector. It's this vector here. It's just a differential. of the parameterization x. Remember, a differential is a linear estimate of the change of the function. X is position. So, this function here is telling me where I am over this amount of time dt. My position actually changes from there to there, because this function is actually curved, right? I mean, it's not entirely, flat thing. So my actual change, you might call the increment in my position, is what I have in blue there. But the linear approximation of that increment is the differential. That's, in other words, based on derivatives of this function at the point where I actually am. Based on those derivatives, what is our linear estimate of the increment? And so that's just the differential. It's the same differential we've talked about in other contexts. The difference is that here the differential is a vector, and the reason the differential is a vector is because my function is a vector-valued function. Yeah, is everybody okay with that? So this dx vector is, so it's a vector that's kind of tracking this little piece of curve. It's not exactly the same as the little piece of curve, but it's going in the same direction, at least initially, as the piece of curve. The length of it is, based on the speed that we were going, the actual speed might vary a little, but probably not very much. So the length of this vector should be about the same as the length of the little piece of curve. It's just the curve might pull away a little bit. Yep.
Would you mind clarifying what's the difference between the dx vector and directional derivative?
Well, so directional derivatives asks a different question. Directional derivative says, suppose I'm in the domain here, over here, and I decide to start moving in with some velocity. And then what's the corresponding change? Well, here, there's really is only one direction to go, right? So what I'm trying to figure out is, okay, as I step over that little amount there, dt, and what I'm momentarily going to call E1 dt, just to make it look like a vector, right? So given that change in the input, dx is the corresponding change in the output. So it's kind of a directional derivative, but we don't really need to think of it that way because it's a differential of the output. Yeah. Anybody else? Okay. All right. Yeah. So what's the relationship between this input change and the output change? Hey, good news. We already did chapter 4. We know the relationship between input changes and output changes. The relationship between input changes and output changes is that the input change is turned into the output change by way of the derivative transformation, right? The derivative transformation of the parameterization. Right, the derivative transformation of that. And a little bit of algebra in here. I can factor out that dt. That's just a scalar. I'm left with derivative transformation applying to a standard basis vector. That's what, your first reaction is going to be to call that a partial derivative because that's a standard basis vector. And then you realize there is only one input variable. So it's just a derivative. It's the plain old, good old derivative of the parameterization. And and of course the derivative is the velocity. So nice punchline, dx is velocity times dt. Now, I know that this is a standard physics thing, right? Displacement is velocity times time. And I'm super good with, if you want to interpret it that way, that's fine, right? The displacement is velocity times time. The reason I went through this calculation is because I wanted to lay some groundwork. We're going to need to go through calculations kind of like this in the next section where it's not as obvious, where there is no sort of physics point of view on it. And so I think it's important to get accustomed to the idea of thinking of this as a derivative transformation acting on an input vector to give you an output vector and working through the algebra of derivative transformation, just for, as a warm-up problem, you might say, for what we're going to see in the next section. But anyway, yeah, displacement is velocity times time. Sure. No problem. Okay, now, why were we computing dx? Reminder, what we really wanted to know, going back over to, well, no, I guess this is a good picture to draw on. What I really want to know is what's the relationship between that length, ds, and this length, dt. It's really size that I'm interested in. If you're interested in the mass of that little piece, you need to multiply density times length. I don't really care how it's oriented, right? If I know the mass per unit length of something, whether it's pointing up or whether it's pointing sideways is irrelevant to computing the mass. I just multiply mass per unit length times length, right? So we made this observation that the ds scalar, that's the length of that little piece of curve, is closely related to the dx vector. Specifically, the magnitude of the dx vector is ds. Right? So we just computed dx. Its magnitude gives me ds. And so I end up with this, again, pretty believable formula. ds is equal to speed, magnitude of velocity, times dt. Okay. All right. And so we're done with our pullback calculation. Here's how pullbacks work. Now, for line integrals, if you want to compute some line integral, maybe you want to compute how much snow you're about to shovel. Hopefully not. Right? Maybe you want to compute the mass of some rod. Maybe you have any of a number of other examples you could dream up where there's something that accumulates over some curve in space, or a curve in R2, either one, right? Any sort of a scalar line integral. Just remember that ds is magnitude of velocity times dt. Plug in your parametrization. Don't forget that position is a function of time, so x is the parametrization. And you just did yourself a pullback. And you have turned a line integral, a multivariable calculus, scalar line integral over some parametrized curve. It sounds real complicated. You just turned it into a Calc 1 integral from A to B. Super easy. Lots of shortcuts. Integration by parts, all that good stuff, right? You just compute it. Everybody happy? Okay. Right. Okay. So, again, don't forget your stretching factor. That's the super easy thing to miss, right? Real easy to accidentally oops the stretching factor. You've got to make sure to remember to put that in there. Okay. All right. So here's a example. How are we doing on time? Okay. All right. Suppose I want to compute the mass of a rod. At this point, in fact, we don't really care what the example is. We've already seen how this line integral construction will apply to a lot of examples. So for whatever reason, we want to compute this integral, in this case because it's mass of a rod. So, mass density per unit, density per unit, mass per unit length is our integrand. How do we compute this thing? Okay. We need to parameterize our curve. Always the first step, right? Your curve, parameterize it. The parameterization is what you plug in for position when you do the plugging in. The parameterization is what you take the derivative of to get your stretching factor, by magnitude. So you've got to have the parameterization. That is number one to compute a scalar line integral. There's a few exceptions every so often, but number one is parameterize that curve. Okay, so what is our curve? Our curve is the top half of the unit circle in R2. Let's see, do I have a picture of this? No? Okay, let's draw a picture. Here's our XY plane. There's the top half of the unit circle. And how do we parameterize the top half of the unit circle? Well, so again, this goes back to Chapter 2, right? We saw a lot of techniques for how to parameterize back in Chapter 2. So I'm a big believer in the graph parameterization. That would have been an option here. Totally fine to use the graph parameterization. What I'm doing here instead, you'll notice, is what you might call the polar graph parameterization. Right? So here I write down the equation in polar coordinates, r equals 1, and then plug that in, right? Which is morally equivalent to the graph parameterization. So anyway, hopefully everybody remembers how to do this parameterization. So there we go. This is what we're going to be plugging in. This is what we're going to be using to pull back this integral. It's going to help us rewrite x in terms of t and to rewrite ds in terms of dt. It's all going to come from this parameterization. Alrighty, details. Now our formula up here tells me I got to compute the velocity and then take the magnitude, right, to get the speed. So the speed is our stretching factor. So here you go, magnitude of velocity. Well, velocity is x prime. So we've got to take the derivative of this function, which of course we do coordinate-wise, which gives me this. Now I got to take the magnitude of that vector, and very conveniently, that's 1. Right? So ds, which is speed times dt, is just dt. That make sense to everybody? Okay, so now let's see, what do we do with all the x's and y's in here? Let's see, our density, what color did I use down here? Green, okay. So our density is x squared plus 2y squared. Okay, x squared plus 2y squared, right? This is x squared plus 2y squared, but don't forget now, x is cosine t, and y is sine t. So specifically, I want to compute density at the location x, x having been computed at the time t. So x is now a function of t by way of plugging in our parameterization. Right? So that's x, and that's y. Everybody on board? Okay, so let's see here now. Our function. It's easy to lose track of this. Function is x squared plus 2y squared, and that makes this turn into cosine squared plus 2 sine squared. And trig observation, you can rewrite that very nicely as 1 plus sine squared. Our dt, of course, comes along for the ride, and as promised, we have turned this into a Calc 1 problem. And by the way, you'll notice that there is the question of how do you actually compute this integral. I guess arguably this is Calc 2, but anyway, Calc 1 and 2 are prerequisites for this course. I am going to assume that you're good at computing integrals. It's necessary, right? Multivariable calculus unavoidably uses a lot of single variable calculus. We've been asked to make sure, by other departments, that, hey, it's important for students to continue to be good at single variable calculus after they get out of single variable calculus class, right? And so different departments were complaining that, students get to us and they kind of know some multivariable calculus and differential equations, but they can't do integrals anymore, right? So these are going to come up. I'm not going to, go to awkward contortions to avoid any challenging integrals. I mean, I'm going to avoid the really, really hard integrals, right? But standard kinds of integrals like this one, you need to make sure that you can do. Does everybody remember how to do this one? A lot of people a little rusty. Might want to brush up. The trick on this one is a half-angle formula. I think half-angle formulas are really, really good things to have memorized for just such an occurrence. Those of you who come to my office hours might recall that half-angle formulas have come up several times in our office hour discussions. Okay. By the way, when I say half-angle formulas, I mean just for sine and cosine. You don't need to know half-angle formulas or double-angle formulas for, cotangent. Just don't bother with those. Okay, but sine and cosine, very important. Okay, so there's another example in here, And you guys can read this example on your own. It's not terribly different. It's a depth of snow example, so we go back and we use this. We already talked through this development. All that this exercise or this example does here is show how to use a parametrization to crank this out. So I'm going to let y'all guys do this on your own. Okay, and again, a bunch of exercises. Okay, so next section. So we, by the way, concerning the exam, we have now made it through 5.8. And we have, as I'm seeing it here, 8 minutes left, which means there's no way we're going to finish 5.9, right? So the fair game material for the exam, per my email yesterday, up through 5.8 only, not 5.9. That said, we definitely need to use those 8 minutes, so here we go. We're going to talk about scalar surface integrals. And it's so similar. Right, we're not going to be able to finish this in 8 minutes, but it's not going to take us an hour either. I mean, this is a pretty quick section because it's so similar. It's the same idea. It's, suppose we have this, again, dimensionally awkward situation. I want to compute, let's say, the mass of a curved sheet of metal in space or something. And so there's this temptation to say, well, it's a triple integral because it's in 3 space. But it's not, right? It's a 2-dimensional thing. It's not a 3-dimensional solid. And likewise, it's tempting to say, well, if it's a 2-dimensional thing, use a double integral. But it's not in the XY plane. It's not in the YZ plane or the XZ plane. We need to account for how it fits in 3 space, but it itself is only 2-dimensional. So morally equivalent problem, dimensional awkwardness. Everybody see that? Any questions about this observation? And yet, look, it remains. I mean, you could totally talk about, if you want to compute the mass of something, mass is still an accumulating quantity. The total mass on this thing is the sum of the mass on that slice plus the mass on that slice plus etc. You can still chop it up, add it up. Right? So this is now going to be, let's count integrals again. We had single, double, triple integrals. Then we added in scalar line integrals. This is now number 5, scalar surface integrals. It's a qualitatively different kind of Riemann sum. But it's still morally a Riemann sum. We're still going to do, strategically, chop it up, add it up. It's the same kind of situation. Okay, so again, maybe we're computing mass. Maybe this is a hillside. And there's plants growing on this hillside, some kind of a grass, let's say, and I want to, for whatever reason, I want to compute how many blades of grass there are on this hillside. And it's tempting to say, well, just look at a little piece and multiply the number of, the blade density on a little piece of area and multiply it by the area of the hillside. But for one thing, what is the area of that hillside? That's a little problem. All right? And for a second thing, what if the blade density is not constant? Maybe, as would be physically plausible, there's less grass at higher altitudes and more grass at lower altitudes. So what if the density is not constant? Hard problem. Okay, so what we would like to do, looking at a little piece, and let's see, let me zoom out one notch. This little piece of area right there. That little piece of the surface. On the one hand, I'm going to need to know its area, because if I'm going to multiply some sort of a, mass per unit area or number of blades per unit area or bugs per unit area or whatever it is, whatever sort of a density I'm going to multiply by, quantity per unit area is going to have to get multiplied by area. So I need to be able to get my hands on what is the area of this little piece. But also, I'm going to need to be able to get my hands on the location. Where is this little piece of area? So pick some point in there. And, I need to know where it is. Because, again, blade density might depend on altitude. Well, altitude where? Altitude on this piece. This piece is at what location? I need to have a spot that I can nail it down at. Okay. Alrighty. And that said, here's how we write an integral. This is just a Riemann sum right here. But this says, at this location where I am, where that little piece of area is, We have some sort of an integrand. Again, maybe it's mass per unit area, maybe it's blades per unit area, maybe it's bugs per unit area, whatever. Depending on the application I'm interested in, right? So some sort of a density that I need to multiply by area, right? So again, if it's mass per unit area, I have to multiply that by area to then get mass. If it's blades per unit area, got to multiply that times area to get the number of blades on that little piece of area that I then add up to get the total. That I then take a limit of to make the round off errors go away. Okay. So, this construction, morally equivalent to what we've seen previously, but different because of the context. So we have to call this a new kind of an integral. I call this a surface integral. I think for pretty obvious reasons. It's an integral that's taking place on a surface. I stick in this prefix that this is a scalar surface integral. Again, I for the moment, I'm just going to vaguely refer to, foreshadowing. There will be another kind of surface integral that we will talk about that's very important, that is importantly different from this thing. Right? And at that time, I'll talk about why this term scalar is a useful distinction to pick out this particular one. Right now, it's just terminology. Don't worry about it. We'll get to it later. Okay, so scalar surface integral. Again, I think this notation is pretty reasonable, right? We have a little piece of area, delta S. Well, we abbreviate that with ds. Right? Not a unreasonable choice. We're doing a summation. Now, this is a summation over an area. There's two different directions to go on this area. On the one hand, there's where are you kind of in that direction. On the other hand, there's where are you kind of in that direction. There will be two indices. If you were to slice this thing up, a pair of scissors or whatever, and write down labels on where these things are, you'd have sort of an I telling you how far you are in the blue direction and a J telling you how far you are in the green direction. Right? So since there's two indices, I think it's reasonable to use two integral symbols. As usual, you got to tell me what the domain is. As usual, we'll just write it as a subscript, just as a notational convenience. So again, very plausible notation, very common notation. I encourage you to use this as you're developing your Riemann sum. Go ahead and use integral shorthand. It's convenient, right? But again, don't forget that when you write stuff like that down, what you're really saying is you're really saying Riemann sum. Right? Very importantly, these are Riemann sums. Okay. Okay, so how do we compute these things? We've already talked about the applications, various applications. You can use it to compute math, something like this. How do you compute? Let me just say something super quick about that in the remaining 30 seconds we have. We find ourselves in a, again, familiar situation. We have a domain we don't like. We don't like it for dimensional reasons. It's two-dimensional, but I don't like that it's not living in a two-dimensional world. So let's view it being an image of something that's in a two-dimensional world. If only there was some way to view surfaces as images of, let's say rectangles in the UV plane, we would be set up to do a pullback. Oh wait, yes of course, we have done that. This is simply a parametrization of a surface. So more details to follow, but our big foot in the door on computing surface integrals is going to be to pull back through parametrizations of the surface. Okay, and that's a good stopping point. We will